we start with a square, which is really a head-on view of a cube which begins to rotate. Our first impression of a rotating 3-cube is that of squares sliding. This is the revolving door illusion. If we rotate the three-dimensional cube about a different axis, we get parallelograms and rectangles, images that we readily interpret as the shadows of a rotating three-dimensional cube. But now we rotate in four-dimensional space. Our first view of a rotating four-dimensional cube gives us the impression of three-dimensional cubes sliding, the revolving door illusion in one higher dimension. If we stop the four-dimensional rotation and revolve around an axis in 3 space, we get something which resembles a wireframe model, like the frame of a box kite. But now we rotate in a different plane in four-dimensional space. This is our first really good view of a four-dimensional cube. It has 16 corners, 8 on the red cube, 8 on the green cube, with corresponding corners connected. But as we rotate in 3 space, we see that one three-dimensional face is still quite flat. We rotate again in four-dimensional space, this time leading to truly general position. At almost any instant, the 4 edges that come out of one of the corners have no 3 lines lying in a plane. Stopping our four-dimensional rotation, we show a three-dimensional spin around an axis where we see the red cube and the green cube interlaced. At the end of our four-dimensional rotation, we fold all the way back, come back to 3 space, continue back to the plane, and end at a square. Viewing objects in three-dimensional space, we are aided by the devices of perspective. As we rotate a 3-cube in perspective, we see each of the 6 bounding squares as the smallest, furthest away square, and then again as the largest, closest square. This is not the top view of some 2-dimensional creature swimming in on itself. It's a rotating 3-dimensional cube, and we are quite used to these perspective distortions. But now we go to 4 space. We change our perspective, and we proceed to walk around that 4-dimensional cube. As we walk around, we see each of the 8 cubical faces as the smallest cube when it's furthest away, or the closest cube when it's largest. This is not a 3-dimensional creature swimming through itself. It is the shadows of a rotating 4-dimensional cube. This is the best rotation, with the red cube now largest, now flattened out, now turned inside out as the smallest furthest away cube. And if we become comfortable with rotations, every once in a while we see a rotation which confuses us once more. Rotating directly toward us and away from us, we find another very strange view of the rotating 4-dimensional cube in perspective. At the end, we go back and end at our 3-dimensional cube. In addition to projections and rotations, we can use the device of slicing. Slicing a square by an edge parallel to one side gives us a segment for a while. Corner first gives us segments which grow and come back off ending at a corner. We can use the same technique to slice a 3-dimensional cube. Parallel to one face we get a square for a while. Edge first we give rectangles, which grow and come back off ending at an edge. Most interesting is corner first. What do we get halfway through? We can see that a bit more slowly. Triangles which become cut off, so that halfway through we cut each of the 6 bounding squares in precisely the same way. We obtain a perfect regular hexagon halfway through the cube. We can use the same techniques to slice a 4-dimensional cube. We position our 3-dimensional knife parallel to one face to get a cube for a while. Square first, our slices are square prisms that come back off, ending at a square. There are 2 more symmetrical ways of slicing a 4-dimensional cube. Edge first gives us triangular prisms. Halfway through, a hexagonal prism, coming all the way back off, ending at an edge. Most interesting, most challenging. What do we get when the slice comes through corner first, along the long diagonal? We can see that more slowly. A small tetrahedral pyramid, which grows until it hits the vertices and becomes truncated, cut off, so that 3/8 of the way through we have 4 equilateral triangles, 4 regular hexagons, 1 hexagon exactly halfway through that red cube. This is a semi-regular polyhedron already known to Archimedes. Halfway through, we cut each of the 8 bounding 3-dimensional cubes in precisely the same way. We get 8 equilateral triangles fitting together to form a perfect regular octahedron, a Platonic solid. We complete our tour of the 4-dimensional cube by showing slices which go off at a point not situated at the center of the screen. One last pass. Tetrahedra, tetrahedra cut off, in the middle, the octahedron. Tetrahedra cut off the other way, coming back off, ending at a point, completing our tour of the 4-dimensional cube.